Thank you, Leo, for this introduction. I also would like to make this opportunity to wish everybody healthy, peaceful, and successful 2026. So I work at the LEM3 University of Lorraine, France. And so working as a research engineer, in fact, I have a double mission. The first is my research, and my research belongs to Department 2 of LEM3. We have three research departments. And so from the title, you will see the domain of Department 2 is microstructure engineering, processing, crystallographic, anisotropy, and behaviors. And one of the hallmark expertise of this department is crystallographic study. And so for my technical service, I belong to these platform, Micromat. We have also three platforms. And for this platform, we have SEMs, mini. We do a lot of EBSD, TKD, and also we have FIB, and we have a TEM, we have X-ray diffractometer, and we also have heat treatment facilities. And so also one of the strong expertise of this platform is crystallographic characterization. And so benefit from this, I would introduce this powerful tool with three case studies. And so the first two related to study on metallurgical processes of materials for phase transformation and for recrystallization. And the third one is how can we streamline TEM operation using these expertise. And so first, I would like to express my sincere gratitude to my colleagues at LEM3, University of Lorraine. Special gratitude to Benoît Bossir and Jean-Jacques Vandenberger. They are modest but great crystallographer and software maker, and also hardware maker, and also my two former PhD students. And I also would like to express my gratitude to the collaborators in different countries. And so now I come to the first case study. This is regarding to phase transformation from FCC phase to sigma phase in a medium entropy alloy. And for this study is from part of PhD work of Luda Wang, and we have a paper published last year concerning this topic. So in this work, we use the material, these medium entropy alloy with these elements and such composition. After solution treatment, after preparation of the material, we have a microstructure look like this. So it was equiaxed green, but a lot of annealing chains inside, because this material is low stacking fault material. I would like to say it's ultra low stacking fault energy material. And from a synchrotron diffraction pattern we see, we have only FCC phase. And after that, we made a cold rolling with 70% reduction. The microstructure looks like this. So the equiaxed grains become elongated along the rolling direction. And the important thing is we see a lot of slip bands with these band contrast, the EBSD map, we see clearer these black lines, and outlined with black lines. And if we can have a look, this is slip bands. We can have we count the angle of these shear slip bands with regarding to the rolling direction, we can see they are in this range. And I will show you something later with this characteristic. And so after that, we made reheating, or we'll call it recrystallization. And we can see this is under inspection of synchrotron diffraction. And we can see at the beginning, the spectra looks like this. Is mainly composed of FCC phase, but with certain HCP phase. And this phase is introduced during rolling. When we increase the temperature with this heat treatment regime, and we can see when the temperature increases, this HCP phase disappears. But we have, when the temperature reaches 900 degrees C, we see additional peaks appearing. And this peak corresponds to the so-called sigma phase. And these peaks intensify with the increase of the temperature and reaches the maximum at 1000 degrees C after half an hour annealing. And then when we continue to increase to 1100 degrees C, and then we find this peak disappears. Then when we made cooling, we see the spectra here, we have only FCC phase. When the material re-experiences the temperature range for sigma formation, we did not have the sigma phase. According to phase diagram, normally the composition of this material, we should not have the formation of a sigma phase during heating from an equilibrium state. And so this means the sigma phase was the formation was strictly related to the high density of defects generated by cold rolling. So then we know the transformation is from a present FCC phase, and the sigma phase is a topologically close-packed tetragonal phase. And so how the transformation occurred through atomic process with the aid of crystal defects. And then we see with only synchrotron, we cannot see microstructure. We like to know where these sigma phase form. And then we made heat treatment, and we made ex situ examination by EBSD, SEM EBSD. And so we heat the material with the same heating rate. It's very quick. And then to 900 degrees C, and these three temperatures, we cool the material in liquid nitrogen to freeze the heating microstructure, and then to do examination. And so we see at 900 degrees C, the material is still preserved the morphology of the cold rolling state. And then we had a closer look on the slip bands, the dark area. We can see the white dots already formed on these regions. And you see they did not form homogeneously throughout the microstructure, but mainly located in the slip bands region. And we know these parts should be full of crystal defects. And then when we increase the temperature, you see the microstructure is halfly recrystallized. And still, the formation of the sigma particles is not homogeneously everywhere, but mainly on slip bands region. And then we continue to increase the temperature, the material is fully recrystallized. And then we can see slight coarsening of the sigma particles. And now if we held it for half an hour at this temperature, we see we have a secondary recrystallization. Some parts, the grain grow much more than the part full of sigma particles. And we also find the sigma particles quotient. And so with this information, we see the formation of the sigma phase is really related to the crystal defects. We'd like to know what kind of defects, how they interacted. And then we use SEM ECI electron channeling contrast imaging and to study the precipitation and also the defects. And we see here are the sigma particles, and we have twins, annealing twins. And also we have these white lines. And these lines correspond to the stacking faults. And so we can see all these sigma particles are intersected by the stacking faults from on different orientations. And if we have a closer look with TEM, you see here is one sigma particle and then around full of stacking faults. And so the question is, from this structure chain to this structure, how the stacking faults and dislocation help this atomic process, because the transformation is really ultra rapid, not normal. And then to really know the atomic passage from here to here, we need to have a correlation between these two structures. And so we made a texture analysis, and we see for the stacking faults on the slip bands, this slip plane should be 111 plane because it's FCC crystal structures. Then we plot the FCC pole figures here, and be careful, it's not expressed in the rolling coordinate system. It's in these microscopic microstructure, this coordinate system. And we also searched a little bit and find that the 001 plane of sigma phase has some correlation with the FCC plane. Interestingly, only these two pairs of 111 plane copied by this 001 plane, and not the other 111 plane here, you see? And these two pairs pose the orientation really corresponds to the angle range of these sleep systems. And so the 111 planes. So that means we can make an atomic link between the two structures. So we can go deeper to do analysis to see how the passage happened from this structure to this structure. We use stacking of for sigma phase, we use this 001 plane, and for FCC phase, we use this 111 plane, but we use 3 planes with stacking fault here. Okay, and then we constructed the unit cell with these 111 stacking for FCC phase and with 001 stacking of the sigma phase. We see the similarity between these two structures. And now we are interested in the atomic configuration, how the atoms arranged on each phase. Then we put the FCC 111 plane here, you see like this. And if we outline a unit plane cell, it looks like this. And if we put the sigma A prime plane here and B prime plane here with different colors, these different colors only resolve the layer, but not atomic species. And then we put them here. You see, for the blue one is this configuration, and for this is this configuration. If we put them together, is exactly this 111 plane. And then the question is how these 111 plane removed these atomic atoms to make such motif. then we have to consider this transformation is helped by stacking faults. And so if we put the 111 plane of the FCC phase here, we see if we can make this part of the 111 plane from position A to position C under the Burgers vector of this partial dislocation. We see here we have a distorted area. And then if we continue to make this part to next C position with this Burgers vector, partial dislocation, and then we can see we further enlarged this distorted area. Then we repeat these two processes here, and then we see we can outline a motif. You see this motif here is exactly this motif. So that means the transformation from FCC to tetragonal is made by the activity of the stacking faults. And this also allows us to explain why these two planes are copied, because on this area we have high density of stacking faults. And so you see, without any in situ atomic scale characterization technique, we can resolve such kind of atomic passage for phase transformation. So you see how wonderful the crystallographic analysis. And so this work allows us to really use these, I say forensic tool, because after that we can study to much deeper and to represent the process at the atomic scale. Okay, so this is the first example. For the second example is how I will show you how we use this tool to resolve the mechanisms behind the recrystallization process in alpha phase in titanium aluminide during high temperature deformation. And so this part of our work is from a second thesis work, and so it's Fengming Qiang. And we use the material is at this composition. And so in the phase diagram, you see the material is here. And we heat the material to this alpha phase zone at temperature. Here you see the temperature is very high. We can only do it in glibos or in kilatometers. And so after holding to homogenize the microstructure, we made compression, and then we made water quenching. Nothing to do with me, I hope. Okay, and then you see during this deformation, we use this strain rate and to different strains and the true strains until here, and then the material experienced such kind of microstructure change. For us, we like to know what mechanisms behind each step. And so for this study, we can encounter two difficulties. The first difficulty is you see the phase is only exists, the single alpha phase only exists at this temperature. And we have to do examination at room temperature. Then how to have the information of pure sigma phase. And with this, we use a reconstruction of high temperature phase from low temperature EBSD measurement using this magic Melangin software. It's also made in our lab, in our department by colleagues Lionel Jamin, Nathalie J, tutored by Michel Humbert. And then we have a second problem. We can artificially reconstruct the single alpha phase But if we do examination with TEM or with SEM, anyhow, we cannot examine the dislocation configuration, because anyhow in the sample we have, you see at room temperature we have the beta phase, we have the gamma phase. Then we use the crystallographic tool. So it's intragranular misorientation axis analysis. And this is not invented by us, but we made application. And so I have to introduce a little bit this method. You see with material one, the initial shape is here, we make a banding. Very simple. With banding, we have these plastic deformation and macroscopic shape change to this form. And internally, we should know these shape change is realized by accumulation, generation of dislocations. So in such kind of a configuration. And you see, in this case, we have only one type of dislocations, and is age type dislocation. And you see, by this formation of dislocation, this part of the sample is orientation is disoriented from this part of the sample. But with EBSD measurement, we can resolve this rotation angle and also the rotation axis. In fact, you see the rotation axis is parallel to the dislocation line. And people call this rotation angle Tyler axis. And so this Tyler axis is, can be calculated using the Burgers vector B and the slip plane normal N here. And so the method worked like this. We measure we measure the orientation of different parts, and we analyze with the software to have the disorientation in angle and in axis. And then we match the calculated angle with the type of dislocation lines to produced by dislocation, by deformation, and then we can resolve which kind of slip activated. And here I just like to introduce some terminology I will use later. And so you see, this is the age dislocation. And here we the atomic arrangement is like this. And this is the slip plane. And here we have so-called extra half plane. Due to the existence of these, we have this so-called age dislocation. And the Burgers vector is here. Okay. So if these age dislocation in the previous configuration is with high energy, and the thermal effect, they will reduce the energy, and then the dislocation will climb and then form a kind of low angle boundary. And these the existence of such a low angle boundary also make these two paths disoriented. And so also we can describe these with the angle and axis. And this axis is also the Tyler axis. And now we have to analyze these, we have to do a little bit calculation. And so this is also simple calculation with matrix, with rotation matrix. And so you see, if this part is disoriented from this part, and we can describe this with an angle and an axis. And this axis is the Tyler axis. And in this rotation matrix, you can see is the components are really only related to the coordinates of this Tyler axis and also the angle. And also, if we have these, we can resolve the angle and the axis. Okay, and now back to our material. So you see, when we heat the material to this temperature and then with held it for 10 minutes to homogenize the microstructure, and then we made the water quench to have the initial microstructure before this compression. And we can see the microstructure is reconstructed from the EBSD map measured at low temperature. And then we see composed of coarse alpha grains with structure, hexagonal structure. And the boundary is relatively smooth. And when we do the compression in this, with the progress of the deformation, we see the microstructure changes. And now, with all these changes, we would like to know what happened behind to drive such kind of microstructure change. And so now we made a step analysis. One, at the very beginning of the deformation, we see the microstructure, the change is only at the green boundaries. And so we can see the green boundaries become not at all smooth, but more serrated. We say it's bulged. And this is corresponds to in most time in textbook, it's related to such a bulge is called strain-induced boundary migration. And in this case, it's more this part with low density of defects. That means low stored energy to high density of defects. That means high stored energy part. And so this is more in the category of recrystallization. And then we made just a very simple chem analysis. Feng Ming, she made this. And then from the enlarged, this zoomed picture, you see the situation is exactly inverse. So you see the bulging part is with high density of defects, but in front is lower. And so it's not what we thought strain-induced boundary migration, but it's another category is called stress-induced boundary migration. Then we try to analyze this here, which gives all these defects, which system activated to have these boundary bulging. Then with this example, we plot the line and analyze the disorientation angle and the axis and plot it here. We see starting these all the values relative to the origin. So the point is here. And so you see, there's a angle. We have a plateau jump, plateau jump, plateau jump, plateau jump. But in any kind of jump, we see the angles are different. But if we have a look of the axes, you see the axes are very close to the D001 axis. And so even with numbers like this, it's very gives something very different. But you see is 2, 1, 1, 12. And so it's close to 001. And then we analyzed all the possible slip mode in HCP crystals. And Feng Ming calculated these Tyler axes here. And then we just make a comparison. And then we see it is this slip, prismatic slip A, and the Tyler axis is 001. And so that means for the bulging, stress-induced boundary migration is due to the activation of prismatic slip. Then this allows us to go a little bit deeper to see how such bulge happen. And so for this, we see this is a compression. This is exactly our case. And when this dimension decreases, this dimension expand. And so in this direction, the material experience a kind of tension. And so we can consider we have two grains here, grain 1 and 2, was this extension in this direction. And then this boundary we see at such high temperature, the boundary link is very weak. And so the boundary becomes broadened. And then when the prismatic slip is activated, they will create a lot of dislocations, and these dislocations will move towards the boundary area. And then with such a weak boundary, the dislocation, and also these boundary works as dislocation sinks. And so once one dislocation moves into the boundary region, we have a one-step extrusion of the boundary. And if we have a large amount of dislocations go in this area, and then we finally have this bulging. And so this allows us to see clearly how stress-induced boundary migration happened. But in any case, such kind of dislocation configuration is not energetically economical. And so with the thermal effect influence, the dislocations will climb to form such kind of low energy configuration. And this is called polygonalization. And this corresponds exactly to what we see was before in the bulging area. We have, if we plot the misorient on this line, we see the jump is such a formation of such kind of boundary. And so it's in A place, B place, C place. You see jump, plateau jump, plateau jump, plateau jump. And so this allows to really clearly resolve how this bulging happened. Now we continue. When we increase the deformation to these for true strain 0.01, and then we see there are more bulgings happen, but we also see a lot of these white line is with angle between 3 and 15 degrees form along the boundary area. Is some enclosed, you see enclosed the bulging part. And so Fengming made a very careful analysis in a large area, and then she made a statistical account, and she find that 40% of such boundaries was the rotation axis 001. And so this we have already known it is corresponds to the prismatic slip. But we have another two, and they have a large population for these axes. You see, it's 1/3 of the population, and for these axes we have a quarter. And so, in fact, such kind of boundary, the x and y value is not fixed. It's from 0 to 1, something like that. And then what behind such kind of the formation of such kind of dislocation? No, the axis. And so we made a comparison with the other slip mode. We see there's no fit. That means it's not realized by the activation, possible activation of the other slips. And so we have to enlarge a little bit our search scope. And so we extended this wonderful method. And so we thought at this stage, maybe we have another slip activated. We should allow these things to happen. And then, is it possible we put the first slip and then add another slip as a rotation with axis. Yes, it is possible with crystallographic analysis. So you can see here we have a matrix, here we have a matrix, and then we make matrix multiplication. We have the final matrix here with rotation here with the angle and axis. And the axis, we do not know what are they. Okay, and so how we do Fermi did with the first rotation. She used these prismatic sleep, and for the second rotation, she introduced all these possible sleeps. And then here is an example. And we see here we have a bulging and we have a boundary, close this bulged part. And then she made the simulation. You see, we fix the two axes. We just verify varying the angles, and then to calculate the general axis and angle. And so you see, if we plot the axis, it distributed on this orientation line. So you see it's from a pure prismatic sleep to pure basal sleep. And so with these, we could further analyze what happened. And so we say at the beginning, we have the activation of these prismatic sleep. And then we have the activation of the basal sleep. And the boundary area will absorb this basal sleep inside and then make orientation evolution of these two parts. And so it's illustrated here. And then we will have a new boundary with larger angle. And this new boundary, you see, for the first sleep, we have symmetrical tilt boundary, but with absorbing this basal sleep dislocation in, we will form this asymmetrical tilt boundary. Okay, and this allows us to well explain what happened to form such kind of boundary. And now we have a second case. It is here. And then Fermi also tried with all these possible combinations, but she could not find. And then we enlarged a little bit our imagination. We say, okay, when we have the dislocation, the puzzles, the prismatic sleep formed, and then we have these climbing to form the boundary. Is it possible this part of the crystal related to this part of the crystal can be rotated with an axis perpendicular to this ultra half plane normal. And then for prismatic sleep, the direction perpendicular to this extra half plane is this axis. And then she made a combination of these two, and then she made a simulation. You see, varying these two angles, fix these two axes, and then we find the axis falls in this orientation line. And so that means, and we made a further analysis. I have no figures to show here. In fact, the orientation, the trace of this boundary is normal, is exactly parallel to this axis. And so that means this allows us to identify that during this process, there's a boundary sliding. Anyhow, we deform the material at a very high temperature. And so you see, with boundary sliding with this part related to this part along the axis perpendicular to the extra half plane. And then we form this so-called tilt-twist boundary. This is also mentioned in the literature. And so it's very fine. And then continue. deformation we see now, the boundary of the coarse grains now decorated by these fine grains. The question is, these fine grains is from a new nucleation or from already the bulging part, and the bulging part further evolve with the different deformation mode and to increase the orientation difference from the matrix grains. Then a simple pore figure analysis. For example, here we have only one layer of fine grains. And then we see we have two matrix grains, G1 and G2. And we have small domains, D1, D2, D3, D4. You see, but maybe not very clear is here. And then we just simply plot the pore figure of these two parts with the G1 and G2 grains inside. And you will see D1 and D2 orientation is very close to the purple grain. And D3 and D4 is very close to the orientation of G1. And then we say it's not a new nucleation for this kind of recrystallization. It's fragmentation from the parent grains, parent coarse grains. And then we ask question further, for such kind of things, how it happened. And then we made analysis here, only with the pore figures. You see how powerful it is. And you see, this is the parent grain, the red grain. And the small grains here, their orientation very close to their mother grain, but they are physically detached from their mother grain. And so this allows us to see there's a happening of grain boundary sliding. That means either upper layer grains or lower layer grains, they will force in and separate the fragmented part from their mother grain. And with these, we have these boundary region full of small grains. And now, if we continue our deformation to the final deformation, we see the completion of these full part recrystallized, all microstructure recrystallized. And with all these analyses, we can say clearly this recrystallization is a continuous dynamic recrystallization. And starting from stress-induced boundary migration, and then evolving by absorbing additional dislocations of different type with grain boundary sliding, and then from the grain boundary layers, zones to the interior of the coarse grains. And this process repeated, and then until the completion of the recrystallization. So this is the second example. Now I come to my service. How we can aid it by these crystallographic analysis to streamline the TEM operations. And so this is also part of the work of Wang. And the software is already made by Benoit with aid of Jean-Jacques Vandenberger, and the paper is accepted by Journal of Applied Crystallography. We have already volume part, but next month we haven't page. And so if you like, next month you can find the paper. And so you see, for TEM operation, we always need to specifically align the beam with respect to a specific crystalline direction to have a desired contrast. For example, to analyze dislocations, you see, to visualize dislocation, Then we have to position the beam, allow this beam in Bragg condition, more or less, with respect to here is the dislocation, and with the plane here. As the existence of dislocation, this plane is distorted at this area. If we can make only this small part of the plane in Bragg condition, we will have very nice, you see, fine lines of dislocation. And only this plane in Bragg condition, in TM, we call it two-beam condition. And if only this part in Bragg condition, we call it weak beam condition. And I have to specify for TEM, we work at very high accelerating voltage of electrons. So the electron beam with a wavelength very small. And for example, for aluminum, with 111 plane, with plane spacing of this distance, then according to Blagger law, the Blagger angle of this plane, you see, is less than 1 degree. That means if we align the beam with respect to such kind of plane, we just make the plane parallel to, more or less parallel to the beam, then it's okay. But you know, for TM, the beam is here. We cannot turn the beam. We have to turn the sample to search for the good orientation. And so if we do not know the orientation of the crystal we like to study, the search would be a painful search, very horrible. And so it's very time consuming. It consumes the time and effort of the operators, but also consume the exploratory potential of the TM. So at the end, we are fully exhausted. And so we thought we should find some method to help this process. Then comes this work. And so we made a software module to motorize all these process and to make the examination really simple. And so the software module is here. At these, you can download this magic text software. And our module is here, is called TM Aligner. And so with this part, the third example, I will explain very roughly the approach, and then I will use an example to illustrate how to use this module. And so the workflow is like this. First, we need to determine the crystal orientation. And these, either we acquire Kikuchi line pattern as EBSD in SEM, but in TM. And thanks for this magic software, also made in LAM3. So it's an eclectic fantasy. And then we can have the orientation of the crystal. And then if you cannot have Kikuchi line patterns, you can acquire spot patterns. With spot pattern, you can use this commercialized software ASTA to identify to determine the orientation. But Benoit continued since the paper continued to work on this part. Now, yesterday evening, he told me that we can also identify, determine the orientation with spot pattern. And so it's a good news. It will all be in this TM liner. Okay, and then with this orientation, the software will calculate the geometrical relation between the beam, the acquired crystalline direction, that means the reflection plane normal, and the tilt axis of the sample holder. And then the software will tell you how many degrees and in which direction you should tilt your sample to reach the position of the either two beam condition or the zone axis condition. Okay, so the software looks like this inside, and we express all these relation with the pole figure. And so you see, we have different zones with different colors, and these different zones tells us the angle limits of the TM holder, because in TM we cannot turn the sample from 0 degrees to 90 degrees. And so with different zones, either such kind of zone is single tilt, either x direction, alpha tilt, or this is we need two double tilts. So the zones like this, and zones like this, we will never reach any condition. Then we have to abandon, and we have to search something else. Okay, and now I have to explain a little bit sample holders, because we have different sample holders. And so one type of sample holder is we can rotate the sample around z-axis, and this axis is normal to the sample surface. And we can also tilt the samples. This called the gamma rotation, and these we can tilt the sample around the x-axis, and this we called alpha tilt. And for these, we use the pole figure projection on this equatorial plane, and then this is in the software. The beam direction is here. And so if we like, we have a pole here of individual crystalline direction. And the second type of double tilt holder is beta, alpha, beta. And so the alpha tilt is always there. And in this case, the beta tilt is around the y-axis. For TEM sample holder, the tilts are specific. For either gamma tilt or beta tilt, when we rotate the sample, the coordinates, the other coordinate axes, either z, x, or in this case, yx, will not change, will not affect it. But once we rotate around the x-axis, it's the whole stage turns. And in this case, will affect these the other axis. So we have to be careful. For the second case, we select the projection plane like this. And in this case, the beam orientation is here. Beam is here. And then we have the projection of the crystalline direction. And due to these specific rotations, then if you use our software, it's always the tilt or rotation not affected. That means either gamma or beta tilt first, and always alpha tilt the second. Otherwise, if you reverse the tilt, the calculation is not for such kind of operation. Okay, and now I use an example to illustrate how can we use this software to guide our workflow of TM operation. And so we also use the material, these medium-entropy alloy. And then with the initial state, we see we have these equiaxogram with a lot of twins, annealing twins inside. We have single FCC phase. And now we deform the material. And in this application, I will show you how to identify Burgers vectors with this software. And so we deform this material at room temperature with these strain rate and to 2% elongation. And you see, as this ultra low stacking for energy material with deformation, we form not perfect dislocations, but extended dislocations. You see, with stacking faults, these are the stacking fault fringes, and bordered by partial dislocations. And so this configuration is called extended dislocation. And then in this application, I will show you how to identify the Burgers vectors of partial dislocations. Then we need the two beam condition. We used our TEM. It's a very old TEM, or nearly 30 years old. But you see the contrast is wonderful. And then we use a holder is gamma plus alpha holder. And then the workflow is like this. We put in the sample into the TEM, and then heat the filament, and then take bright field image at 0 tilt position. And then we see the image is here, and then we see twin boundaries. And between twin boundaries, we have pileups of these extended dislocation. And so it's a stacking force bordered by two partial dislocations. Just for vocabulary, yes, we will analyze this part. And then I take out this small part here and tell you, here are the stacking faults, you see, with the fringes. And then we call this part, because the movement is in this direction, so we call this part leading partial. This is a leading partial dislocation. And the leading partial dislocation is to enlarge the movement of this leading partial is to enlarge this stacking fault part. And the following part is called the trailing partial dislocation. And the movement of these partial following the leading partial is to restore the plane to the normal plane. Okay, and this is the first. I say something a little bit more. And then now I should analyze the orientation of this part. And then we make orientation determination. For our case, we use our magic software, Euclid Fantasy. And then we take a Kikuchi line pattern here. And we think all these parts should have more or less the same orientation. And then you see the Kikuchi lines. With this software, we immediately have the all angles. And with these all angles, we can make further analysis, because we like to analyze the partial dislocations, the two partial dislocation, the Burgers vectors of this part. Then we first identify the slip plane. And with this, we use trace analysis. And we know for FCC plane, the stacking faults or dislocations are always on the 111 plane. And so we just need to plot the 111 pole figure. And you see, for these pileups, we can see where is the 111 plane trace. You see, it's here, the trace. And so this 111 plane is inclined in the sample. And so we see the upper line and lower line. And now, if we make a trace analysis, you see the trace is here, and we put it here. And now, you see for each pole, it corresponds to the 111 plane, and this pole is given by its normal direction, normal vector. And so the normal vector is outlined by this dashed line, and the plane trace should be here, perpendicular to this dashed line. And then we see this trace is exactly this 111 plane. So how nice our work reduces. And now we will use the Thomson tetrahedron to to continue to reduce the work scope. And this is the homework we have to do before. And so now you see with these tetrahedron, and we have 4 111 planes. And with the indices of this plane, we see is this phase. And then if we enlarge it, it is here. And we know we have only partial dislocations. And so on this plane, we have only 3 partial dislocations as candidates. And so the Burgers vector of the partial dislocations is 2 of these 3. So the scope continue to decrease. And now, which kind of reflection plane we should use? And then Luda also made the homework. He checked with a lot of reflection planes with a big table. Finally, he find these 2 are very nice. And so in this case, we use the so-called very famous G.B criteria. And for partial dislocation, it's a little bit specific because for perfect dislocation, we have a contrast index, either 0 or 1. But for partial, we have 0 to 1, passing 1/3, 2/3. But fortunately, the contrast is proportional to these values. And so the value is larger, the contrast is higher. And so then, if so, he find this reflection plane. And so with pole figure, we found it is here. And it's exactly in the single alpha tilt zone. And for these 2 minus 2, 0 plane, the pole is here. And so it's exactly in the single alpha tilt zone. And I have to explain a little bit because here is the beam orientation. So it's normal to the screen. And to have a 2 beam condition, then where the pole should move, in fact, is moved towards the gray circle because this pole corresponds to the normal vector of this plane. And so if we move it to this, the plane is parallel to the beam. Okay, and so in this case, the rotation is like this. And so for this case, the rotation is like this to reach this gray circle. And now it's the software. But now Benoit added a lot of things. The page changes. It's not this configuration, but you can find all information here. So first, we have to introduce the phase because we need the phase, the diameters to make a crystallographic calculation. And so we should give the correct phase. And now, after that, we have to select which work we like to do. So it's a 2 beam condition. And now we have to enter the orientation with all angles here that we determined. And next, we have to select which kind of sample order we like to use. In our case, it's gamma rotation alpha tilt. And then we have to define the limit. For gamma rotation, there's no limit, but for alpha rotation, we put 40-degree limit. And now we have to select the reflection plane. So for the first case, we select the 111 plane, and you see it is here, the reflection plane. And so we just need to use the mouse to click on this dot. Immediately, you have the software calculates the results for you. And it proposes 2 options, either 2-step rotation or single-step rotation. And so now, Now, Luda, he used the single-step rotation. And so this is a true rotation. This is a calculated rotation. There are some deviation, but this is normal. And then we see now the contrast changes. And then we see for the leading one, we have a higher contrast. For the trailing one, we have a very weak contrast. And so in this case, the leading one corresponds to this Burgers vector. Okay, now for the second case, because for these we cannot differentiate these from these or these from these. And so we use the second reflection. This is 2 to 0. Then we select these. We have the pole figures here. And then we use these reflection. And then the same, we point here. And then immediately we have the solution. And so it's also two, either by two-step or single-step. And so now we continued and we see the image contrast is not very nice, but we see convincingly clear. For the trailing one, we have a higher contrast. For the leading one, we have weak contrast. And you see, that means the trailing one is this Burgers vector. And added for the first results, we ambiguously determined the two Burgers vectors, this and that. And so with these, I finished my talk. I like to express my thanks to these two experimental platform to offer all this work, especially my platform, Macromat of LAM3, and all my colleagues are here, and we are welcome you to collaborate with us for crystallographic characterization. So thank you very much for your attention.
Yeah, thank you, Yudong, for a very impressive overview of the power of crystallography analysis with transmission electron microscopy. I think I can stop the recording here.
Thank you.
Yeah. Stop the recording.